In this session, let us explore into the storage basics, introduction, primary storage, and secondary storage.
Let us have a brief introduction of a storage system. A data storage system is a computer system which is capable of storing data, where the storage component is often referred to as storage or memory. The storage system consists of computer components and recording media that are used to retain digital data using a set of rules called protocols. The digital data can be stored either temporarily or permanently. Based on these, the storage is classified into two types, namely primary storage, secondary storage. What is a primary storage? A primary storage is a memory where a digital data is stored and the data remains until the power supply is present. The computer system's main memory, where the central processing unit, CPU, executes the instructions and data for processing. These types are seen as CPU registers, internal cache memory, L1, L2 and L3, and the externally connected random access memory, RAM. Cache is directly connected to the CPU, RAM is indirectly connected using a memory controller with a memory management unit, MMU. For examples, we have static RAM called as SRAM and dynamic RAM called as DRAM. These memories have faster read and writes. These are called as volatile memory because the data is lost after power is removed from the device. What is a secondary storage? A secondary storage is a memory where a digital data is stored and the data remains persistently even if the power supply is removed. This memory is not directly accessed by CPU. A separate I/O controller is used to which the storage devices are connected. CPU accesses data by transferring the data from secondary memory to primary memory as read operation and vice versa as write operation. For examples, secondary storage devices are hard disks, solid-state drives, magnetic tape drives, floppy disks and USB flash drives. The data transfer is done using storage protocols like PCIe, SAS and SATA. Secondary storage devices has slower read and writes. These memory devices are non-volatile and the data stored is persistent throughout unless instructed. Let us see the protocols used in storage systems. SCSI is called as Small Computer System Interface, is one of the oldest forms of storage interfaces traditionally used in server or workstation class computers. SCSI system is commonly used for secondary storage. Storage devices like hard disks, SSDs, scanners, CD drives and tape drives use the SCSI commands as higher level of storage protocol. The SCSI standard defines command sets and these are used at SCSI mid-layer by most of operating systems. The SCSI adapter, SCSI connecting cable, SCSI hard disk and the SCSI connector is shown in the figure. It has been through many revisions, from SCSI 1 all the way up to Ultra 320 SCSI, which is the modern SCSI interface. There is an Ultra 640 standard, but that isn't common. The 320 and 640 numbers represent MB/s, megabytes per second. SCSI 1 started out 5 MB/s. SCSI is still used in modern servers, but the interface is starting to lose market share to SAS. Most recent versions of SCSI can handle up to 15 hard drives. While the cable sharing mechanism is relatively efficient, there is a maximum theoretical cap of 320 MB/s, but that limit is reduced further by SCSI overhead. It's theoretically possible that 15 modern SCSI hard drives could have an aggregate throughput of 1350 MB/s, so they would be forced to share a 320 MB/s interface. But in the vast majority of applications, where there will inevitably be some random I/O in the hard drives, the mechanical latency of the hard drive seeking data means it's unlikely that an Ultra 320 interface will be fully saturated. PATA. PATA stands for Parallel Advanced Technology Attachment, originally called ATA and sometimes known as IDE or ATOPI. These are seen mostly in older desktop computers. Parallel Advanced Technology Attachment, originally called ATA and sometimes known as IDE or ATOPI, was the most dominant desktop computer storage interface from the late 1980s until recently, when the SATA interface took over. PATA hard drives are still being utilized today, especially in external hard drive boxes, but they're becoming rare. Some cheaper high-end server storage devices have also used PATA. Like SCSI, PATA has also gone through many revisions. The most recent version of PATA is UDMA/133, which supports a throughput of 133 MB/s. Although PATA supports 2 devices per connector in a master/slave configuration, the performance penalty of sharing a PATA port is severe and not recommended if performance is important to the user. The 40-pin connector and cabling is also extremely wide, which is difficult to use in a high-density environment and tends to block proper airflow. The size of the connector also presents problems for smaller 2.5 hard drives, which require a special shrunken connector. SATA. SATA stands for Serial Advanced Technology Attachment, is the official successor to PATA. So far, there have been 2 basic versions of SATA, with SATA 150 and SATA 300. The numbers 150 and 300 represent the number of MB/s that the interfaces support. SATA doesn't have any performance problems due to cable/port sharing, but that's because it doesn't permit sharing at all. One SATA port permits one device to connect to it. The downside is that it's much more expensive to buy an 8-port SATA controller than an Ultra 320 SCSI controller that allows 15 devices to connect to it. The upside is that each drive gets a theoretical 300 MB/s. Current SATA hard drives, however, barely get 80 MB/s, so the bus interface is a bit of overkill for now. SATA uses a small 7-pin connector and a thin cable, which is more conducive to denser installations and airflow. That's important, especially inside a storage array with 15 hard drives, because you'll need 1 port and 1 cable for every drive, whereas SCSI lets you hook up 1 or 2 ports to the backplane that the drives attach to. SATA drives are used in smaller servers and some less expensive storage arrays. Data rates of SATA Generation 1 has 1.5 GB/s, SATA Generation 2 has 3 GB/s. Now, we are into SATA 3 generation where the data speed is up to 6 GB/s. SAS. SAS stands for Serial Attached SCSI, is the latest storage interface that's gaining dominance in the server and storage market. SAS can be seen as a merged SCSI and SATA interface, since it still uses SCSI commands yet it is pin compatible with SATA. That means you can connect SAS hard drives or SATA hard drives or CD/DVD-ROM or burner drives. SAS has a signaling rate of 185, 374, 750, and eventually, 1,500 MB/s. But storage controller technology has historically been rated by actual data throughput, which is lower than the signaling rate. To make these numbers comparable to the numbers listed above, the actual data rates are 150, 300, 600, and eventually, 1,200 MB/s. Note how the 2 lower data rates match up with SATA. Data rates of SAS Generation 1 is 3 GB/s, SAS Generation 2 has 6 GB/s, and SAS Generation 3 has 12 GB/s. SAS connectors are keyed such that SATA devices can connect to SAS, but SAS devices can't connect to SATA ports. The ports and cabling look similar, but SAS cables can be 8 meters long, whereas SATA cabling is limited to 1 meter. The longer cabling support is due to higher signal voltages, but the voltage is dropped to SATA levels whenever a SATA device is connected. SAS is designed for the high-end server and storage market, whereas SATA is mainly intended for personal computers. Unlike SATA, SAS can be connected to multiple hard drives through expanders, but the protocol used to share a SAS port has lower overhead than SCSI. Coupled with the fact that the ports are faster to begin with, SAS offers the best of SCSI and SATA in addition to superior performance. FC stands for Fiber Channel, is both a direct connect storage interface used on hard drives and a SAN technology. First, FC offered data speeds of 100, 200, and 400 MB/s. Native FC interface hard drives are found in very high-end storage arrays used in SAN and NAS appliances, although the technology may ultimately give way to SAS. High-speed FC network storage technology works at 1 GB/s up to 128 GB/s. Fiber Channel provides lossless delivery of raw block data and is primarily used to connect computer data storage to servers. ISCSI stands for Internet. SCSI is a low-cost alternative to FC that's considered easier to manage and connect because it uses the common TCP/IP protocol and common Ethernet switches. Because any network engineer is familiar with TCP/IP and Ethernet switch configuration, and gigabit Ethernet adapters and switches are cheap, the cost advantages over FC SANs are compelling. A 16-port gigabit switch can be anywhere from 10 to 50 times cheaper than an FC switch and is far more familiar to a network engineer. Another benefit to ISCSI is that because it uses TCP/IP, it can be routed over different subnets, which means it can be used over a wide area network for data mirroring and disaster recovery. Most ISCSI implementations use Gigabit Ethernet 1000 base T, but speeds can be scaled to 10 gigabits per second with 10 base CX4 and soon with the less expensive 10 base T using twisted pair Cat6 or Cat7 copper cabling. It's possible to mix Gigabit and 10 Gigabit Ethernet such that a high-end storage array uses 10 Gigabit Ethernet, but the multiple servers fed by the array connect to the switch using single Gigabit Ethernet. The downside to ISCSI is that it is computationally expensive for high storage throughput because it has to encapsulate the SCSI protocol into TCP packets. This means that it either incurs high CPU utilization, not much of a problem with modern multi-core processors, or it requires an expensive network card with TOE, TCP offloading engine, capability in the hardware. ISCSI targets, ISCSI servers. The source of the storage can come in the form of hardware storage arrays that speak the ISCSI protocol, or they can come in the form of software added to a server. A server with ISCSI target software loaded is functionally the same as a hardware ISCSI target, but you can build it on top of any major server OS from BSD to Linux to Windows Server. There are open source Linux ISCSI targets and there is commercial ISCSI target software for Windows. Using a software solution allows you to serve a wide variety of devices as ISCSI targets that can be remotely mounted by ISCSI initiators, ISCSI clients, over TCP/IP. Hardware ISCSI targets are merely dedicated servers specifically designed to act as an ISCSI target, and they sometimes simultaneously behave as NAS devices. ISCSI initiator software is natively included in almost every operating system. AOE, ATA over Ethernet, is the most recent SAN technology to emerge, created as an even lower cost alternative to ISCSI. AOE is a technology that encapsulates ATA commands into low-level Ethernet frames and avoids using TCP/IP. That means it doesn't incur CPU penalty or require high-end TOE-capable Ethernet adapters to support high storage throughput. This makes AOE a high-performance, very low-cost alternative to either FC or ISCSI. Its proponents also boast that the AOE specification fits onto 8 pages, compared with the 257-page ISCSI specification. AOE doesn't use TCP/IP. It isn't a route table technology, but then again, neither are FC SANs. Most SAN implementations don't require routability, and the fact that you might use AOE on a particular initiator or target doesn't prohibit you from using ISCSI. A lot of add-on initiator/target software will support both ISCSI and AOE. Most WAN applications are low bandwidth, so it won't incur a lot of CPU utilization anyway. This means you can use AOE for the high-throughput LAN/SAN environment and use ISCSI for the WAN at the same time without TOE Ethernet adapters. AOE software initiator support is now native in Linux and BSD, but it isn't natively included in Windows, and you'll have to purchase third-party initiators. Coraid, which is a major supporter/supplier of AOE, provided the original FreeBSD device drivers. Now let us see the basic storage types. There are three basic storage types, namely DOS, Direct Attached Storage, SAN, Storage Area Network, and NAS, Network Attached Storage. SAN is an intersection of DOS and NAS. In the picture, it shows an instance of the storage types using different types of protocols. DOS, Direct Attached Storage. DOS is the most basic storage subsystem that provides block-level storage, and it's the building block for SAN and NAS. A DOS system is directly attached to a server or a workstation, without a storage network in between. The performance of a SAN or NAS is ultimately dictated by the performance of the underlying DOS, and DOS will always offer the highest performance levels because it's directly connected to the host computer's storage interface. DOS is limited to a particular host and can't be used by any other computer unless it's presented to other computers over a specialized network called a SAN or a data network as a NAS server. A DOS controller allows max 4 servers to access the same logic storage unit. Protocols used for communication between computers/servers and DOS storage systems are FC, or SATA, or SCSI, or PATA, or SASA. The software layers of a DOS system are illustrated in the figure. The directly attached storage disk system is managed by the client operating system. Software applications access data via file I/O system calls into the operating system. The file I/O system calls are handled by the file system, which manages the directory data structure and mapping from files to disk blocks in an abstract logical disk space. The volume manager manages the block resources that are located in one or more physical disks in the disk system and maps the accesses to the logical disk block space to the physical volume/cylinder/sector address. The disk system device driver ties the operating system to the disk controller or host bus adapter hardware that is responsible for the transfer of commands and data between the client computer and the disk system. The file-level I/O initiated by the client application is mapped into block-level I/O transfers that occurred over the interface between the client computer and the disk system. SAN, Storage Area Network. NAS and SAN are two ways of sharing storage over the network. SANs offer a higher level of functionality than DOS because it permits multiple hosts, server computers, to attach to a single storage device at the block level. It does not permit simultaneous access to a single storage volume within the storage device, but it does allow one server to relinquish control of a volume and then another server to take over the volume. This is useful in a clustering environment, where a primary server might fail and a backup server has to take over and connect to the same storage volume. Because a SAN offers block-level storage to the host, it fools the application into believing it's using a DOS storage subsystem, which offers a lot of compatibility advantages. The SAN may use FC, or Ethernet, ISCSI or AOE, to provide connectivity between hosts and storage. The figure gives an example of a typical SAN network. The SAN is often built on a dedicated network fabric that is separated from the LAN network to ensure the latency-sensitive block I/O SAN traffic does not interfere with the traffic on the LAN network. This example shows a dedicated SAN network connecting servers, application or database servers, on one side, and a number of disk systems and tape drive system on the other. The servers and the storage devices are connected together by the SAN as peers. The SAN fabric ensures a highly reliable, low-latency delivery of traffic among the peers. The SAN software architecture required on the computer systems, servers, shown in the figure, is essentially the same as the software architecture of a DOS system. The key difference here is that the disk controller driver is replaced by either the Fiber Channel Protocol stack, or the ISCSI/TCP/IP stack that provides the transport function for block I/O commands to the remote disk system across the SAN network. Using Fiber Channel as an example, the block I/O SCSI commands are mapped into fiber channel frames at the FC4 layer, FCP. The FC2 and FC1 layer provides the signaling and physical transport of the frames via the HBA driver and the HBA hardware. As the abstraction of storage resources is provided at the block level, the applications that access data at the block level can work in a SAN environment just as they would in a DOS environment. This property is a key benefit of the SAN model over the NAS, as some high-performance applications, such as database management systems, are designed to access data at the block level to improve their performance. Some database management systems even use proprietary file systems that are optimized for database applications. For such environments, it is difficult to use NAS as the storage solution because NAS provides only abstraction of network resources at the file system level for standard file systems that the database management system may not be compatible with. However, such applications have no difficulty migrating to a SAN model, where the proprietary file systems can live on top of the block-level I/O supported by the SAN network. In the SAN storage model, the operating system views storage resources as SCSI devices. Therefore, the SAN infrastructure can directly replace direct attached storage without significant change to the operating system. NAS, Network Attached Storage. NAS is a file-level storage technology built on top of SAN or DOS technology. It's basically another name for file server. NAS devices are usually just regular servers with stripped-down operating systems that are dedicated to file serving. Although it may technically be possible to run other software on a NAS unit, it is not designed to be a general-purpose server. For example, NAS units usually do not have a keyboard or display, and are controlled and configured over the network, often using a browser. A fully featured operating system is not needed on a NAS device, so often a stripped-down operating system is used. For example, FreeNAS, an open-source NAS solution designed for commodity PC hardware, is implemented as a stripped-down version of FreeBSD. NAS systems contain one or more hard disks, often arranged into logical, redundant storage containers or RAID arrays. NAS removes the responsibility of file serving from other servers on the network. NAS devices typically use SMB/CIFS for Microsoft compatibility, NFS for Unix compatibility, or Samba for both. Many modern NAS appliances will support SAN technologies like ISCSI, and you can basically build the same hybrid storage solution using a general-purpose operating system like Linux, BSD, or Windows using your own hardware. The difference between NAS and SAN is that NAS does file-level I/O while SAN does block-level I/O over the network. For practical reasons, the distinction between block-level access and file-level access is of little importance and can be easily dismissed as implementation details. Network file systems, after all, reside on disk blocks. A file access command referenced by either the file name or file handle is translated into a sequence of block access commands on the physical disks. The difference between NAS and SAN is in whether the data is transferred across the network to the recipient in blocks directly, SAN, or in a file data stream that was processed from the data blocks, NAS. As the file access model is built on a higher abstraction layer, it requires an extra layer of processing both in the host, file system redirector, computer, and in the function of translation between file accesses and block accesses in the NAS box. The NAS processing may result in extra overhead affecting the processing speed, or additional data transfer overhead across the network. Both can be easily overcome as technology advances with Moore's law. The one overhead that cannot be eliminated is the extra processing latency, which has direct impact on the performance of I/O throughput in many applications. Block-level access can achieve higher performance, as it does not require this extra layer of processing in the operating systems. The benefit that comes with the higher layer abstraction in NAS is ease of use. Many operating systems, such as Unix and Linux, have embedded support for NAS protocols such as NFS. Later versions of Windows OS have also introduced support for the CIFS protocol. Setting up a NAS system, then, involves connecting the NAS storage system to the enterprise LAN, e.g. Ethernet, and configuring the OS on the workstations and servers to access the NAS filer. The many benefits of shared storage can then be easily realized in a familiar LAN environment without introducing a new network infrastructure or new switching devices. File-oriented access also makes it easy to implement a heterogeneous network across multiple computer operating system platforms. In this example, there are a number of computers and servers running a mixture of Windows and Unix OS. The NAS device attaches directly to the LAN and provides shared storage resources. The generic software architecture of NAS storage is illustrated in the figure. Logically, the NAS storage system involves two types of devices, the client computer systems, and the NAS devices. There can be multiple instances of each type in a NAS network. The NAS devices present storage resources onto the LAN network that are shared by the client computer systems attached to the LAN. The client application accesses the virtual storage resource without knowledge of the whereabouts of the resource. In the client system, the application file I/O access requests are handled by the client operating system in the form of systems calls, identical to the systems calls that would be generated in a DOS system. The difference is in how the systems calls are processed by the operating system. The systems calls are intercepted by an I/O redirector layer that determines if the accessed data is part of the remote file system or the local attached file system. If the data is part of the DOS system, the systems calls are handled by the local file system. If the data is part of the remote file system, the file director passes the commands onto the network file system protocol stack that maps the file access system calls into command messages for accessing the remote file servers in the form of NFS or CIFS messages. These remote file access messages are then passed onto the TCP/IP protocol stack, which ensures reliable transport of the message across the network. The NIC driver ties the TCP/IP stack to the Ethernet network interface card. The Ethernet NIC provides the physical interface and media access control function to the LAN network. In the NAS device, the network interface card receives the Ethernet frames carrying the remote file access commands. The NIC driver presents the datagrams to the TCP/IP stack. The TCP/IP stack recovers the original NFS or CIFS messages sent by the client system. The NFS file access handler processes the remote file commands from the NFS/CIFS messages and maps the commands into file access system calls to file system of the NAS device. The NAS file system, the volume manager and disk system device driver operate in a similar way as the DOS file system, translating the file I/O commands into block I/O transfers between the disk controller/HBA and the disk system that is either part of the NAS device or attached to the NAS device externally. It is important to note that the disk system can be one disk drive, a number of disk drives clustered together in a daisy chain or a loop, an external storage system rack, or even the storage resources presented to a SAN network that is connected with the HBA of the NAS device. In all cases, the storage resources attached to the NAS device can be accessed via the HBA or disk controller with block-level I/O. Assignments. State the differences between a RAM and a ROM. What is a SRAM and a DROM? Show a memory cell for each using CMOS circuit diagram. List out the differences between them. List out all the possible differences between primary and secondary storage. What is a cache? How is it different from main memory? What do you mean by DDR? Explain in brief. Explain how a data is accessed from a secondary storage. What is the role of direct memory access, DMA, in this? Explain in brief why the data access to and from a secondary storage is slower. List the merits and demerits of DOS, NAS, and SAN.
This is the end of the session.